My length is 1e5. The length of 18, again, why I am telling you to check this is because in DP with bitmark, like DP with your numbers, like for example called as digit DP, in that you usually end up working on these string itself. So there can be a slight chance maybe something of that sort can be applied. So yeah, just have a quick check if your string length is itself small, which can be represented in the form of number, but it is not in this case. So we have to deal with strings itself. So for sure we know that maybe we can be using digit DP, but again, as I have told also in previous videos, there's a lot of things in digit DP which we actually have to infer. Okay, this is also there, this is also there, this is also there, and then we apply digit DP. Okay, let's go on. It's just an intuition which we have seen so far. Now we have also given an integer k. Okay, we have an integer k, and we have to return the smallest possible integer after removing k digits from nums. Straightforward. We have to for sure remove k digits from these nums and then achieve the smallest positive integer. Now, very basic way is that I know that I have to remove k digits. I know by default I have n digits. So for sure, if I give you n balls and I ask you to remove k balls, so you will simply say, okay, I will remove any of the k balls. So after removing those k balls, how many balls will be remaining? N minus k, and that is your answer. But you will have to choose what k balls to remove out of those n balls. So basically you are choosing k out of n. That is the reason nck will be the ways to choose your k balls out of the n balls, and after choosing those k balls, okay, whatever remaining will be your answer, and that answer you will try to minimize. It will be nck, which is for sure will not work for our complexity because you can see n is large, and for sure it will never work. Now we will see that how we will solve it. We are still confused how we will solve it. Now for that, no worries at all. Let's take it here itself. I took my example here itself, and then I will see, okay, I have to remove k digits. Each of them is a digit. Now manually I'll go and try. Should I remove this? Okay, so I will go and try here. Should I remove this? I will say, yeah, bro, I can or cannot. What if I remove this? If I remove this, I will get a number 432219. Now, if I ask you, what if I would have not removed this? If I would have not removed this, I would have got a number 14322219. Now, if I ask you, who is lexicographically small? Aryan, why did you come to lexicographically small? Because, bro, if you remembered, I have to generate the smallest possible integer. That smallest possible integer will itself be smallest possibly lexicographically small, and that is the reason I recommended you that okay, it is same way saying that we have to choose a smallest integer or smallest character itself. So 1 is less than 4. This is small. I will compare always the first digits, and for sure you might go and ask, but Aryan, what if we have here 4 and all that stuff? Correct. If you end up converting to a number, then you might end up saying, okay, Aryan, it's a big number. It is a small number. Aryan, it is the same way saying that you have a 4, then you have a 14. You are saying that 14 is less than 4. I'll say, yeah, you are true. 14 is not less than 4. But you forgot one thing. Here, you were able to remove a character, and in this I was not removing character, but I was made sure I will have to remove a character. So what I'm saying, okay, whatsoever is the entire number, if let's say in this I remove one character, okay, then I will have to also remove one character. Okay, if I remove it, so if I remove a character anyway whatsoever apart from the first one, any whatsoever, if I remove any character, then the length will be same, and okay, whatsoever will be the length will be same. But now I can compare the first characters. So although you have to compare as an integer, but then you realized, okay, we know that length will be same, and thus character comparison can go in this. Okay, so we realize that it is not good to remove. It is not good to remove one from here, so I will not remove one. Rather, I will go on to next. Okay, should I remove 4? Again, I don't know that if I would have removed 4, then my number would have looked like 1 3, and if I would have not removed 4, my number would have looked like 1 4 3 for sure. Oh, 4 and 3, it seems good and it seems logical to remove 4. Okay, so I will remove 4, and I had k, I'll remove 4, then I'll go on to 3. Again, you see that what is happening. I'm removing a character and then forming a number and then checking was it good to remove or not. So what is happening in this? Okay, at every character you will go, you will try to remove that character, and then you will build up a string, and then we'll check, oh, is it possible to remove or not. Ideally it is the same with saying you will try for all the possible key places to remove. But you see, kind of, I'm just trying to check that if it is even possible to remove some character or not. Now when I was at 3, so I will just try to remove it. Okay, can I remove it? So I have 1 3 2. Now if I remove 3, so I will get a 1 2 2 1 9. Now if I don't remove 3, I will get a 1 3, and for sure 2 2 maybe something. Again, length will for sure become same. Again, it seems like, oh, it was good to remove a 3 also, so I will remove 3 also. Then again, I will go on to my next character. I'll just try again. 1 2 2 1 9. If I don't remove it, now if I remove it, if I again, this is if I don't remove it. Again, if what if I remove it, so I'll get a 1 2 1 9. If this is what happened when I removed it. Now I'm saying, what if I don't remove it? If I don't remove it, I'll get a 1 2 2 and then the same length, and then the same length. Now if I ask you 1 2 same, but oh, it is different. So it was good when I was removing a 2. So okay, I will remove a 2 also, and then that was the maximum limit which I could have removed, and thus I have got my answer. So far you must have a quick idea of, okay, Aaron, roughly you are trying to compare, and then you are just trying to build a string and then seeing is the string actually less or not. If you go on to do it for every character, then it might end up doing n square. But if I ask you, n square will not work because n is 25. So you will try to optimize it. Now when you're going to try to optimize it, what you are realizing, you realize that why, again, if I ask you why this number, why this bottom string was large than the above string. Because if you remembered, after this, in this bottom string, if you continue, after the bottom string you had a 1, which you are actually, okay, you are removing a 2, thus this was being shifted, and thus it was becoming something like above string. So you found out by seeing the pattern that it was good to remove this when you knew you had a smaller crater to the right. It was good to remove this when you knew you had a smaller crater to the right. It was good to remove this when you knew you had a smaller crater to the right. Oh, now you realized it was good for you to remove this character when you got to know that you had a smaller credit to the right. Now, every of this is the concept which we have studied and learned so far. Now we have to apply it in a more algorithmic way. To be make sure, like we'll make sure it will be under O of n or O of n log n, because beyond that we cannot go, else it will not work for time complexity. Now we came back again and we'll start off from the very beginning. Okay, I will have 1. I can push it because I don't know, maybe again, I should only remove 0 provided I have k, and provided I have a smaller number than 1 ahead of k. Now, if I am k, if I go and search for a small number ahead of k, that will be time. Like I will have to take off n time. So I'll not do it. Maybe in future, if I will get that number, I will come back to 1 and I will remove the 1. So again, if I am at 1, I'm looking for a 0 to actually remove 1. But right now, I don't think I may or may not get. So I'll just simply continue. I am at 4 now. If I'm at 4 again, I might remove 4 if I get something smaller than 4 in the future. Now I am at 3. Oh, I am at 3. So I should remove large number recently what I have got, which is more than 3. And also have the strength. I have the strength of 3. So I can remove 3 elements for sure, which are actually more than 3 but are before 3. So before 3 is already whatsoever I have here. I will start removing things which are before 3, and also which are before 3, and also which are more than 3. So I will remove 4. Okay, only one character removed. Then I know, okay, it is the 3 chance, so 3 will be here. Then again, so 2 will come. Now I still have 2 chances left. I will start removing anything which is more than 2, but before 2. So okay, yeah, I can see I had one thing, so I will have 2. Then again, I will get a 2. Okay, I can simply put in here also. I can simply put in here also, although I might say, okay, it is more or less same, so I might keep it as it is. Now I might go on to 1, then I will be landing at 1. 1, okay, I will check. Do I have something which is more than me and before me? Yeah, I had two. So I will start removing. Okay, I will remove one of the twos. So ideally, I should have kept removing, but my k has finished. So I was only able to remove one. What if my k would have been 4? So I would have two chances left. So I would have removed this two also. But unfortunately, my k was just 2. So I will just remove this one, like remove one of the twos, and then I will have to push my one. Now, no k remaining. So whatsoever is coming in, we will have to keep on pushing it. I will keep on pushing it. And thus, this is the thing final which I will get after removing everything which was high in number. Now, you might say, Aryan, it seems greedy. Yeah, it is greedy because you are actually seeing, okay, if you have a smaller thing, you are removing the larger thing. It is greedy. But what is the operation? What is the data structure you should apply? Data structure is simply that, okay, what operation you were doing? Whenever you were at, let's say, this 3, you are checking whatsoever is at the top of your data structure, and then you are removing that thing from the top of the data structure. Now that can be simply a vector also, because you can know that removing a thing from vector and pushing a thing to a vector in the end is O of 1. But this exact same phenomenon is also performed by stack. So if I just shift this up and make it vertical, this is also what the stack does. Okay, top and push and then pop. So if like this, both the operations are O of 1 in stack also. So okay, to be more generic, I will say, okay, I can use a stack in this case to remove any element and to push any element. So far you have just realized what you are doing. Okay, you are applying greedy, then you are applying doing operation with stacks so as to perform the most efficient operation, and you will just keep on pushing the elements. If you have a k, if you have a smaller element, so what will happen while your stack is not empty? So while your stack is not empty, let's name the stack as s, and your current element, let's say your current character c, if it is if it is less than the stack dot top, and also your k is more than 0. Again, imagine that I'm iterating on all the characters of the string. Let's say, okay, let for example auto c in your num. Then I will say that while my stack is not empty, I will keep on removing the element from the stack, and also I will only remove if my current character which I have right now, it is less than the stack top. Then I will remove that stack top. I'll do a stack dot pop, and for sure I have utilized one removal, so I should reduce my k. Now you will see that with this, it seems awesome to look. Okay, the answer I will get. For sure, I will have to get all these characters back to a string. So I will get, when I will be getting all these characters back from a stack, I will be getting a 9, 1, 2, 1. So as you can simply see, I have to reverse it. So as to get a 1 to 1 9. So I will just reverse it and get a 1 to 1 9. So what happened, that if I just continue, I can simply say that while my stack is not empty, I'm just grabbing out all the elements. So I can initialize my string answer and say it is an empty, and then I will simply say answer plus is equals to s dot top, so as to grab the 9. So 9 will be added, then 1, then 2, then 1. So and then again s dot pop to remove from the stack, and then you have got the answer but in the reverse form. So this is the answer but in the reverse form, and then you can simply reverse this answer, answer dot begin, and then answer dot end. So you have just reversed the answer, and then you will get this answer, and you can simply return the answer. Now if you do this, you although are correct but by the first test case, that's it. You are not correct by the other test cases. How? Because you might end up missing something, but so far you have just thought of, okay, and make sure that this answer plus top for corrector, this, if this is a corrector, again make sure if this is a corrector, then this operation is O of 1. If this is a string, it is a O of n plus m operation. So make sure you use it wisely and you know what you are doing so as to not exceed the time complexity. Now coming on back, you will see that your code looks something like this. But if I go and apply the same logic on this example, what will happen? Let's see. So I had, again, I will apply the same operation. I will have a 1 in the very beginning. Then I will encounter a 0. Okay, I'll encounter a 0. if, as you remembered, you're encountering element which is less than the stack, which is at the top of the stack, so you have to remove that element. If you remove that element, you will actually remove this and you will be pushing it in zero. Okay, zero. And again, I had only one chance and I used that one chance for one removal, which is I removed this specific one. So I'm just done with chance, so I will have to get everything as it is. So you will see, okay, as it is. So you will see when you will get this into a string, so you'll get a 0, 0, 2, 0. Again, you have to reverse it. By the logic, you have to reverse it. So we'll get a 0, 2, 0, 0. Ideally, this is a leading 0. So this is what I should actually return, which is 200. This is what actually I should return, which is 200. So you will say, Aryan, that makes sense. That makes sense. That makes absolute sense. But how will you do? Okay, simple. That when you are actually doing it, which means before reversing, right? Before reversing, what I was doing, I was landing onto this. Sorry, I was landing onto this index. Okay, first non-zero character from the end, that will be my ending index. Ending index. Right, so I can take this as a substring, from index 0 to index as ending index. This will be my actual answer substring, and then I can reverse this specific substring only. So that is what I can do. So what I will do in my actual code itself, again, this is the edge case we realized from the example. In interview, you will not get the example. So if I come back, I know that this will give me a string which can have an ending index. I have to figure out the ending index. So after this, which means in this line itself, what I will do, I will initialize a variable called as ending index. Let's remove this ending index. By default, it can be anything. Let's say it is 0. So then I will go on from the end of this answer string. So I will just say int I is equals to answer dot size minus 1, and then I is greater than or equal to 0, and then I minus minus. Now I have to find the first index from the end, which is not 0, and then that will be my ending index. So I'll just say if answer of I is not equals to 0. If it is not equal to 0, again, remember, it is a character because it is a answer is a string. Then I will simply say that, bro, this is my ending index. This is my ending index. So ending index will be I itself. And then I should break it from here itself because I wanted to know what was the ending index. I should not go beyond much further. I'll just break it from here itself. So by this logic, I have got the ending index. So now I cannot reverse a simple answer string because answer string would have been changed. Answer string is a string now from index 0 to ending index. So now if I just write answer string will be nothing but answer dot substring from what character, from 0 to ending index. Now if I am putting at ending index, so length from 0 to ending index will be ending index plus 1 will be the length. Again, this is how the C++ works. You have to pass an index and the length. So this will be your actual answer string, and then you can reverse the answer string. Now you can simply return the answer. Now, okay, everything again seems completely fine, that this will work. Next example will work. This will work. What? Okay, what about this? Okay, 1 0. Okay, let's put it 1 again. I can simply put it 1 again. I will have a 0. Oh, 0 is less than 1. So okay, remove this, you will get a 0. Again, you still have 1k remaining because 1k you used to remove 1, but still 1k is remaining. So what you will do? Oh, that's a quick question. That if you ended up removing stuff, let's say for example, what I could have done. Okay, if would have a stack, I would have 1. Then in order to, I will push it because it is more than top of the stack. I will again push it 3, again push it 4, again because I'm just pushing it because there is no one which is before me which is more than me, right? Okay, then I'll push in 5, then I'll push in 6, and so on and so forth. Again, these kind of stacks are also called as monotonic stack because you will see that this stack pattern is for sure always will be increasing, so there is no question like, okay, Aryan, what if my current element, what if, okay, like this is a 3 but my next element is a, let's say, 9, so let's say it is a 2 but my previous element is also, let's say, 2 here, so sorry, it is, let's say, 4 here. So as in, like, it will always be in a fashion that it will be increasing itself, which means that I will not say that, bro, let's say if I take this example, so if I have a 1 4 and 3, so I will never say that, okay, bro, Aryan, you had a 4, you ended up removing this specific 4, but Aryan, if you had a 2 here but then a 4 here, will it be possible, bro? if I had a fashion like this, if I had a 1 4 2, then for sure when 2 would have come in, it would have removed 4 already, right? So this kind of thing, when you are actually dependent upon your top of the stack, it makes sure that you will always be increasing. Now coming on back to this example, my k was 2, I could not remove anything because everything was as it is, but still you know that you have to remove something. If I give you a 1 2 3 4 5 6, so it is kind of 1 point like 123k. This value is one like in number form it is 123k. So as to make it small, you have to remove something for sure. Ideally, by our greedy logic, we did not remove anything. Ideally, what should we remove now? For sure, last two digit. If I remove them, because I know why I'm only moving last two and not any starting two or middle two, because I know it has been came out from the greedy logic. So anything, it will be like it is monotonic, which means this entire stack is actually increasing. So highest value will be in the end. So remove the last k values from the end itself. So I'll remove the last k value from the end. Now I'll get this values. So now this value had become 1023, 1234. So this is your answer. So now you remembered, okay, if I have a k, okay, if I cannot remove some values, if I have my k still left, then I will remove the top k values. So I will have to modify my code and say that, okay, if I had done the popping and stuff, still there can be a chance my k was remaining. So while my k is more than 0, while my k is more than 0, and my stack is not empty, my stack is not empty, then I will simply remove from the top of the stack, which is stack.pop, and I will reduce my k, and I will reduce my k. And with this fashion, I will be removing the last k values from the stack. And ultimately, you saw that if we come back to our main example, that in the last we still had to remove one of these zeros because we had one remaining k. So ideally, we will be removing this one k. Okay, this all thing from the stack. Then we will get nothing from the stack. So our answer string will be empty string. Reverse will also be an empty string. So if this is the empty string, is my answer empty string? No. If your answer is empty, then your answer is 0. So another edge case. Another edge case is that in the last, if your answer is an empty string, then your answer is actually a 0 string. That is what you have to return. So this is your entire code, how and what we have built up. This is your entire code of how and what we have built up. That is how you actually approach a problem. Now code is pretty simple. If I go back now, I'll show that, okay, we just simply go on to the characters as exactly I showed that, and then like I'll go on and check, okay, while not stack dot empty and my stack top is more than my c and my k is also there, then I will simply remove from the stack and then reduce the k, and then whatsoever I have the current element, I'll push that in the stack. Then at this point, if my k is more than 0, then I'm reducing my k and then removing from the top of the stack, as what I've told. Here also, for safety and especially for the production conditions, make sure that you add a condition while not empty. That is, make sure to put in for safety check. Now I will go on to my string. I'll check and get all the elements from the string, from the stack to a string, and then I will find the ending index so as to remove the ending zeros, or ideally saying leading zeros. Because again, why I'm saying ending zeros, because the stack is right, sorry, the string is right now reversed. That's the reason I'm removing the ending zeros, because after reversing it, it will become the leading zeros. So then I will get the ending index, and then I will just grab the substring from 0 to ending index. Again, length will be ending index plus 1. That's the reason I have put this. Then I will reverse it, and I have a quick edge case, and then I can return the answer. And that is how you can simply solve it in O of n time, because you are going on to all the characters just once, and space also, because you're using a stack, that will be O of n space. And that's how you can simply solve it. Cool. Again, that's a bit tricky question, and you will have to encounter much edge cases, but this is the beauty of this question, using stack, also called as monotonic stack, and we applied the greedy approach to solve this. Cool. You can watch the video, latest video in the comment section, and you can like to let me know how you liked it. Bye bye.